So, in last few classes we have covered a number of direct solvers for matrix equations, and as promised we will move to iterative solvers. But before moving to iterative solvers, we will look into few definitions and few properties associated with matrix algebra, especially on eigenvectors, eigenvalues and positive definiteness of matrix, and how real symmetric matrices are special in that context. We will look into these things in next few lectures, and then we will start discussing on iterative solvers, because to appreciate the application of iterative solvers and their mathematics behind iterative solvers, it is important to cover these topics. So, we will start our discussion with eigenvalues and eigenvectors of a matrix. So, the idea of eigenvalues and eigenvectors comes first with ordinary differential equations, which is represented as a matrix equation, or a system of ordinary differential equations where each of the variables are given as the rate as a rate equations, and rate of each of the variable is linear combination of other variables. So, which is as the equation system given here y 1 prime. So, for example, it can be rate of change of y 1 with respect to time is a combination of y 1, y 2 to y n, y 2 prime is similarly a combination of y 1 to y n, and that goes up to y n prime. So, all these derivatives are linear combination of the variables y 1, y 2 to y n, and that is why we can write this set of equation, as y prime is equal to a y, where y is a vector now, which consists y is equal to this vector y 1, y 2 up to y n. So, what we can see that this is a rate equation, that is rate of change of y vector is a linear combination of the values of the different variables inside y vector, and we can see increase in y is a linear combination of components. So, this example particularly we are giving y as a term of as a y prime as a rate of change of y with respect to time, and when we will go to iterative methods, we will see rate of, we will start with a guess value of y, which will solve some equation a y is equal to 0, and this y prime is the amount by which we are going to correct the guess value to achieve a right solution. So, we will discuss it in detail in later classes. So, now we got an equation system which is basically, as I wrote, can be written as y prime is equal to a y, and in matrix form this will be written as y prime is equal to y a y, and now the question will be how to solve this equation system. So, we will start with a assumed form of the solution, and this will be similar as, for example, if I have an equation of dx dt is equal to Cx, a single variable rate ordinary differential equation or rate equation. The solution becomes straightforward, x is equal to e to the power c t. So, similarly, we will assume a form of the solution here, where the variable the vector y is one vector x, which is different coefficients in front of e to the power and e to the power lambda t. So, it is a linear combination of e to the power lambda t, we can say like that. And now, if we substitute this into the matrix equation, what we get? Y is equal to e to the x e to the power lambda t. Therefore, y prime is equal to lambda d dt of the right hand side part. So, lambda x e to the power lambda t, and we have the original equation which is y prime is equal to a y. So, if we further substitute it y prime is equal to a y and substitute y which is x e to the power lambda t and y prime which is lambda x e to the power lambda t, we will get lambda x e to the power lambda t is a x e to the power lambda t, e to the power lambda t as non-zero can be cancelled out from both sides, and we will get an equation a x is equal to lambda x. And this particular equation is an equation for the eigenvalues and eigenvectors of A, and lambda is called eigenvalue of matrix A and the corresponding x is called an eigenvector. We will see eventually for an n by n matrix there can be multiple values of lambda and multiple eigenvectors coming into place. We will quickly see that through an example. So, we jump to the example which is I 1 prime is minus 4 I 1 plus 4 I 2, I 2 prime is 1.6 I 1 plus 1.2 I 2. So, we assume I 1 and I 2. So, this again we can write this equation as we can assume a form of I 1 and I 2 which is x 1 e to the power lambda 2, x 2 e to the power lambda 2. So, this is again can be represented as a matrix equation I 1 I 2 prime is equal to minus 4 4 minus 1.6 1.2 I 1 I 2. Now, while we seek solution of this equation, we start with e to the power lambda t form and I 1 I 2 is x 1 x 2 e to the power lambda t. And now, if we substitute that, we will get that a x, and a was as I wrote earlier. So, it is I 1 prime I 2 prime is equal to minus 4 4 minus 1.6 1.2 I 1 I 2. So, this is the matrix A here. So, we differentiate it and we will get the eigenvalue equation from x is equal to lambda x, and which is minus 4 4 minus 1.6 1.2 x 1 x 2 is lambda x 1 x 2. Now, we bring the left and right hand side matrix into the left hand side part and deduct the value lambda, which is, so here lambda we can also write this lambda is lambda into I 0 0 I, because this will be anyway multiplied with x 1 x 2. So, we subtract lambda from the left hand side matrix and we get a equation A minus 4 minus lambda 4 minus 1.6 1.2 minus lambda x 1 x 2 is equal to 0, which is A minus lambda I, I am sorry I just made a mistake here. So, this instead of writing this, I think this can be written as to be correct here, this should be written as lambda into I, or this particular value, or lambda into 1001. So, we subtract lambda into 1001 from the left hand side and we get minus 4 minus lambda 4 minus 1.6 1.2 minus lambda x 1 x 2 is equal to 0 0. So, you can quickly check that if we get a matrix A minus lambda I x is equal to 0. Now, what is this matrix? This is nothing but a null space equation. If A minus lambda I is a non-singular matrix, x will have a trivial solution, x is equal to 0. If A minus lambda I is a singular matrix, then we will get non-trivial null space vectors, non-zero null space vectors for A minus lambda I, and x will be non-zero. And in case x is equal to 0, the equation the first equation we started with, where we assume the form I 1 I 2 is equal to x 1 x 2 e to the power lambda t, this I 1 and I 2 both are 0 and the equation is 0 is equal to 0. So, it becomes a trivial equation which we started. So, we will seek form of lambda which will make a minus lambda I singular, so that we can have non-zero x. This is interesting in a sense. Now, we are trying to find out a singular matrix and we will find its null space, which will be the solution in this particular case. So, we write for singular a minus lambda I, x is non-zero, x is a non-zero null space vector. So, the solution is obtained as finding null space of a minus lambda I, and the null space is non-zero only when a minus lambda is singular. So, it is also finding the values of lambda for which a minus lambda is singular. So, we have to find a value of lambda for which a minus lambda is singular, and this value will be called as the eigenvalue. And for this lambda, the null space of a minus lambda I will be the eigenvector. So, we will look into the next few steps, that for singular a minus lambda I, determinant is 0, and that will give us an equation from which we can find the values of lambda for which a minus lambda is equal to 0. So, determinant of a minus lambda is equal to 0, which gives us minus 4 minus lambda 4 minus 1.6 1.2 minus lambda is equal to 0. So, minus 4 minus lambda into 1.2 minus lambda plus 4 into minus 1.6 is equal to 0, which is lambda square plus, sorry, this is 2.8 lambda. Lambda square plus 2.8 lambda plus 1.6 is equal to 0, and this is which we will solve, we will get lambda is equal to lambda plus 0.8 and lambda plus 0.2 is equal to 0. This is a quadratic equation of lambda or for higher dimension of A, for 3 into 3, 4 into 4, n into n A, this is a higher order polynomial of lambda, and this is called characteristic equation, which is a polynomial of lambda is equal to 0, and we have to find out the roots of the polynomial. So, we get lambda plus 0.8 into lambda plus 2 is equal to 0, which gives, and each of this lambda is the eigenvalue, and we get the eigenvalues which is minus 0.8 and minus 2. So, now the next steps will be to find out the eigenvectors. So, what we will do there? We will take this matrix, maybe we go back to the, let me go back to the previous slide, will, sorry. So, we got minus 0.8 and minus 2 is equal to 0. We will take this value minus 0.8 and substitute it in this equation, for example, minus 0.8 here. So, minus 3.2 and 2 x1 x2 is equal to 0, which is a null space equation, because this matrix is singular when we have the value lambda is equal to 0.8 minus 0.8 or lambda is equal to minus 2. So, if I substitute lambda is equal to minus 0.8, this is a singular matrix. So, x is equal to 0, we will have one non-zero x value for one particular value of lambda, and that will be the eigenvector. So, look into it. So, we go ahead with eigenvectors minus 0.8 and minus 2, and the null space equation for lambda is equal to minus 2 is 2 4 minus 1.6 3.2 x1 x2 is equal to 0, and we can quickly see that now the columns are dependent on each other. The second column is nothing but first column into minus 2. So, it will have a rank which is not a full rank matrix, rank will be 2 minus 1 and 1. So, you should get one null space, vector, and solving the null space vector is 2 1. Similarly, for lambda is equal to minus 0.8, the second eigenvalue, we get the equation minus 3.24 minus 1.62 x 1 x 2 is equal to 0, and we can also see that this is again also the columns are dependent on each other. So, it will have rank 1. So, we will have n minus r, which is one null space vector here. So, the eigenvector comes as x 1 x 2 is equal to 1.8. Therefore, the complete solution, we assumed a form of the solution which is I 1 I 2 is equal to e to the power lambda t x 1 x 2, and x 1 x 2 is the eigenvector. So, we will get one solution which is e to the power 2 t into 2 1, and other solution will be e to the power 0.8 t into 1.8, and both are the solution of a linear equation. So, the final solution will be their linear combination, and that is why we can see the complete solution is I 1 I 2 is 2 1 e to the power minus 2 t, and this is one eigenvalue, and it 1.8 e to the power minus 0.8 t, this is another eigenvalue, and these are the eigenvectors. So far so good, but we can do is that we can, for the rate equation, we can find the eigenvalues and eigenvectors, and the final solution will be a combination of the eigenvalues and eigenvectors, and it can be any linear combination of that. Here we are putting 2 1 1.8, but we can use some other, we can multiply them by some constant. So, it can be C 1 into 2 1 e to the power minus 2 t, C plus C 2 into 1.8 e to the power minus 0.8 t. It is a linear combination of the eigenvectors multiplied, each one multiplied with the eigenvalue. Okay. So, now the process, though it is solution of a rate equation which involves multiple variables, this process also gives us something regarding a matrix, that is the eigenvalue of a matrix, which is something which subtracted from the diagonal elements of the matrix gives us a singular matrix, and the solution x which is the null space, and eigenvector x which is the null space of that singular matrix, which is eigenvector. So, you get eigenvalue and eigenvector, and they have several other application apart from solving rate equation. Rate equation is one very important thing, but they have other applications as so. There are several other properties of matrix which are based on the eigenvalues and eigenvectors. We will discuss them later. However, rate equation is one of our primary drive here, because we will soon start working on iterative methods, which is we will discuss, which is similar as the rate equation. Change of value of one variable is dependent on the other variables. So, this property of eigenvectors and eigenvalues, or this particular usage of eigenvalues and eigenvectors in the back is important as the backbone of the iterative methods, at least few of the direct iterative methods, which will I say it will come to that later. So, now we can make few very important observations in order to obtain the eigenvalues and eigenvectors, or through the processes that we have followed to obtain the eigenvalues and eigenvectors. Eigenvalue problems originate where rate equations for a set of variables are expressed as linear combinations of those variables, and that is why, as I tried to make this point earlier. So, they are related with iterative methods, because the rate of the change of one variable will be linear combination of other variables, at least for the direct iterative methods. So, however, the next observation is only the square matrix has eigenvalues, and this is because if I have n variables whose rate is dependent on those n variables only. So, you get n equations and n unknowns, and that is why this will give me a square matrix system. So, only a square matrix will have eigenvalues. Finding eigenvalue is finding values of variable lambda for which determinant of a minus lambda is equal to 0, because the lambda we have to solve the equation a minus lambda I x is equal to 0, where x is a non-zero variable. Therefore, a minus lambda I must be a singular matrix which needs determinant of a minus lambda is equal to 0. This will lead to a characteristic equation which is a polynomial equation of lambda. If, and we have seen that, like if I express determinant of a minus lambda I will get a polynomial of lambda, and if A is an n into n matrix, the polynomial will have or degree of n. So, order of n will be equal, or rank of n is equal to the degree of the polynomial n, degree of the polynomial getting here. In R n, the polynomial, if A columns of A belong to R n, the polynomial is of nth order, and the first term of the polynomial will be minus lambda whole to the power n. And why is it so? Because whatever we get into this equation as lambda 1, lambda 2, lambda n are the roots of this equation. This equation can actually be written as a 1 1 minus lambda is here, then a 1 2 etc., then a 2 1 into a 2 2 minus lambda, and then the remaining terms, then a 3 3 minus lambda and the remaining terms. So, when we will try to find out the determinants, we will get a term minus lambda whole to the power n, which is the first term of the polynomial equation. Okay. Roots of the polynomials are different eigenvalues, true, because we are solving, if we get a polynomial p lambda, we are solving, if this polynomial is p lambda, we will solve p lambda is equal to 0, which is nothing but a minus lambda is equal to 0. A minus lambda is a polynomial of lambda which is equal to 0. So, you have to find out roots of the polynomials, and they can be, they will give different eigenvalues, and there can be maximum n distinct roots, because it is a nth order polynomial. So, it is also to be mentioned that there can be n distinct, maximum n distinct eigenvalues, there can be less than n eigenvalues also, then some of the eigenvalues are repeating. For example, I have an equation where 2 and 2 both are eigenvalues. So, there is only one eigenvalue, both eigenvalues are 2, there is one eigenvalue which is 2, which is repeating 2 times, lambda minus 2 into lambda minus 2 is equal to 0, the polynomial is lambda square minus 4 is equal to 0, for example, I got something like that. There can be less than n eigenvalues, then some eigenvalues have been are the repeating roots of the polynomial. Eigenvalues can be real or complex, true, because it is a polynomial equation, and we will look into fundamental theorem of algebra later, which says that there can be complex roots of polynomials, and we know that from even from quadratic equations we can see that there can be complex roots of a quadratic equation which has real values. The coefficients are real, but the roots are complex, which is possible. Abel-Ruffini theorem tells that it is possible to analytically find roots up to polynomial of degree 4. Beyond that, we need computer methods, and this is important. So, eigenvalues needs a computer methods in most of the cases, or through trial and error or through approximation, we need to find out the roots of the polynomial equation. So, and if you look into MATLAB or BLAS or LeanPack or all the linear algebra libraries available, you will find codes available for or functions available for finding out eigenvalues of a large matrix, and they are little complicated computer programs, because they are trying to solve the equation, the polynomial equation in an iterative method through trial and error method, and analytically it is not possible to find out these solutions if the degree of polynomial is more than 4. Finding eigenvalue is finding the values of variable lambda which will make a matrix A minus lambda is equal to singular. True, because if A minus lambda is not singular, then eigenvectors will be 0, trivial, and this will be a trivial solution, and the rate equation will also have a trivial solution, 0 is equal to 0 in both sides. So, it is important to find lambda which will make the matrix singular. A singular matrix has an eigenvalue lambda is equal to 0. So, this is I think needs little more discussion. For example, we wrote determinant of A minus lambda I is equal to 0, which gives us A minus lambda I is singular. Now, if A is singular, determinant of A is equal to 0, that gives us lambda is equal to 0. So, determinant of A minus lambda I, which is determinant of A, is equal to 0. At least there is one lambda which is 0, which will give determinant of A to be 0. So, a singular matrix will always have an eigenvalue which is 0. Eigenvector is the null space vector of A minus lambda n. We have seen it in the last example, because A minus, because we are solving, I should write, because we are solving A minus lambda I x is equal to 0, and this x is eigenvector. So, it is null space vector of A minus lambda I. Each distinct root of polynomial which is determinant A minus lambda is equal to 0 introduces one dependent row or column in A minus lambda I. So, what happens, for example, again we will write the equation in the echelon form. So, the matrix in the echelon form will have A 1 1 A then a non-zero value, then A 1 A 2 2, then 2 non-zero values, then A 3 3, and remaining all these terms 0, etc. So, the matrix, so the characteristics equation will be minus lambda, and it will go so on. So, if one lambda is one root of this equation, then A 2 2 this minus lambda term, this will be 0, because the determinant has to be 0. So, if this is 0, this column, this is a 0 pivoted column, and that will be a dependent row or column. So, one distinct root will include or will enforce one dependent column in A minus lambda I, or one dependent row in A minus lambda I, by making the pivot of A minus lambda I 0. So, each distinct root of polynomial A minus lambda I will introduce one dependent row or column in that matrix. Therefore, each distinct eigenvalue will reduce the rank of A minus lambda I from n to n minus 1. So, rank will be reduced by 1. So, what will be the dimension of the null space here? Rank of the null space here 1, because there will be only one null space vector, n minus 1, only one null space vector. Therefore, each distinct eigenvalue will be associated with one eigenvector, which is null space of A minus lambda I. Eigenvalues which are repeated roots of the characteristic polynomial will have multiple associated eigenvectors as the dimension, because they will introduce more pivots, more 0 pivots. So, the dimension of the rank of the matrix will reduce by more than 1, and the dimension of the null space will be n minus rank, which is more than 1. So, there will be multiple associated eigenvectors, and this idea is called geometric multiplicity of eigenvectors, that with repeated roots of the polynomial we get multiple eigenvectors associated with these roots. And we will see for real matrices the number of eigenvectors associated with with real symmetric matrices, the number of eigenvectors associated with one repeated root is the number by which the root is repeating. For example, lambda 3 is repeated in 3 times as 3 roots of the equation of a polynomial p lambda is equal to 0. So, lambda is equal to 3 will have 3 associated eigenvectors, that is called geometric multiplicity of the eigenvectors for repeated roots, that is also observable here. So, we will try to introduce eigenvalues and eigenvectors, and we will look into more detail of the properties of eigenvalues and eigenvectors in the next few classes. Thank you.